Hello there. Welcome to the Sleepless Scientist, where your imagination can roam even while you rest. Wherever you are, nestled beneath a warm blanket, curled up in the soft quiet of your room, or lying still with only the hush of a fan or the breath of the night to keep you company, ask yourself this: what time is it for you right now? Midnight? 3 a.m., just after the last train of thought left the station? Tonight, let's go somewhere your body can't follow but your mind is invited to explore, a place where clocks tick unevenly, where a second might stretch into 1,000 years or vanish before you can name it. And don't worry, you probably won't survive this, at least not in the traditional sense, because tonight you'll bend through time, ride paradoxes like waves, and gently slip into the folds of what science still cannot explain. Before we begin, if you find your way back to the waking world, do leave a whisper of your journey in the comments, and subscribe if you'd like to return again. Now close your eyes and listen. You are floating through a timeless expanse where stars are not scattered but carefully hung, each one a ticking mechanism, a glowing gear in the cosmic clock. And somewhere on Earth, two twins are born under the same moonlight, identical in every way, heartbeat, hair, fingerprints. You follow them through their early years, playing by the creek, building forts, dreaming beneath the stars. Then one of them, let's call him Theo, boards a spacecraft. He is launched far beyond the atmosphere, accelerating faster and faster until he's a blur against the black. He loops around the nearest star and drifts back. For him, it feels like a few years at most, but for his brother Elian, still on Earth, decades have passed. His face is lined, his hands are slower now. Theo returns home younger than the man who stayed behind. You stand between Sumamiyakian, in them, stunned. They are twins, but no longer the same age. This is the twin paradox, a strange child of Einstein's theory of relativity. According to the equations, time dilates when you move quickly, not metaphorically, but literally. The faster you go, the slower time ticks for you compared to someone standing still. Einstein's math checks out. Atomic clocks flown on airplanes run ever so slightly slower than ones left on Earth. GPS satellites, drifting high above us, must correct for time dilation to avoid being off by kilometers. And yet, how can this be real? How can two people share a childhood and diverge in age? Some scientists have tried to explain it away by pointing out the asymmetry. Only one twin accelerated and decelerated. The math, they say, stays clean, but others scratch their heads. If time is relative, they whisper, who gets to decide who's right? You walk through a corridor of clocks now, all ticking at different rhythms. One floats slowly, thickly like syrup dripping. Another races ahead, blurring into a stutter of sound. It's not just science fiction, it's physics. Mainstream, tested, confirmed. And it messes with everything we think we know about cause, effect, and memory. Now tilt back, and let's explore a little fringe. There's a theory, softly spoken in corners of theoretical physics, about time crystals. Not the kind in fantasy novels, but structures that repeat not in space, but in time. Matter that beats like a heart, eternally without using energy. They break no laws, but they shouldn't exist. And yet in 2021, researchers at Google claimed they created one inside a quantum computer. You reach for one of these time crystals now, and it shimmers with impossible rhythm, ticking not forward but outward. And then you realize, the closer you get to the edge of understanding, the stranger it becomes. Scientists still argue. Whether time is a dimension or an illusion, you hear someone say behind you. The voice is warm, amused, fading into mist. Whether it flows like a river, or whether it's just a trick of perception, you drift now into a memory that never belonged to you. It's the year 1905 and you're in Bern, Switzerland. A young patent clerk, dark hair, sharp eyes, scribbles equations between reviewing clock designs. He's annoyed that trains don't agree on what now means between cities. His name is Albert, and the world is about to change. He imagines riding on a beam of light. What would the world look like from that point of view? The result becomes special relativity, the idea that time is not fixed, not universal, but elastic. You walk past his cluttered desk and see the paper on the electrodynamics of moving bodies. It's filled with symbols, yes, but it's also filled with paradox. Because now, causality wobbles. Two events can disagree on which came first. Simultaneity, the idea of now, is shattered. You glance again at the twins, one aged by gravity, the other by velocity. And you, dear listener, age not at all in this dream. You remain right here, suspended between seconds, floating in the corridor of time. But now the walls dissolve, and you feel yourself pulled towards something even stranger. A sealed box, a soft meow, and a question no one has ever answered without arguing. But that's for the next chapter. You drift gently toward the next ripple in logic, where the universe plays a quiet, cruel game behind closed doors. You arrive in a small, nondescript room. No sound, no wind, no time. In the center of the room sits a perfectly ordinary box. No bigger than a microwave, no stranger than an old shoebox at first glance. And yet, what lies inside has caused generations of scientists to sweat, argue, and surrender. You move closer. Written faintly on the lid in neat German script is a name you know too well, Schrödinger. Welcome to the paradox that purrs. You crouch beside the box. It's sealed shut, but in your imagination you peer inside anyway, suspended. In a strange limbo, half curled on the metal floor, is a cat. Is it alive? You blink. Is it dead? You blink again. And the unsettling truth is this: until you open the box, until you observe it, the cat is both dead and alive, both curled in breath and still in final sleep. This is not metaphor, it is not poetry, though it sounds like it. It is a paradox at the heart of quantum mechanics, the science of the very small. In the 1930s, Austrian physicist Erwin Schrödinger proposed the thought experiment as a critique, even a mockery, of the newly forming Copenhagen interpretation of quantum physics. According to this view, particles like electrons or photons don't have definite states until they are observed. Until someone looks, they exist in a superposition of all possibilities. To demonstrate the absurdity of this, Schrödinger imagined a cat trapped in a box with a deadly setup, a radioactive atom, a Geiger counter, a vial of poison, and a hammer. If the atom decays, an entirely random quantum event, the Geiger counter detects it, triggers the hammer, breaks the vial, and the poison is released. But quantum theory tells us, until observed, the atom is both decayed and not decayed, so the cat becomes both dead and alive. You can feel it, the ridiculous elegance of the whole idea, something so tiny as a subatomic decision rippling outward into the fate of a living thing. In this strange halfway world, the cat meows and is silent. It paces and lies still. It lives and does not live all at once. And only when you lift the lid does the universe choose. Mainstream physics has embraced this unsettling truth. Quantum mechanics, as bewildering as it is, works. It predicts things with extraordinary accuracy. Lasers, transistors, nuclear reactions, even the smartphone you might have used today, all built upon a paradox we cannot resolve. But how can the universe be? Undecided? How can observation itself define reality? Some scientists still argue whether consciousness collapses the quantum wave function or whether the universe does it all on its own, randomly, impersonally. Others suggest an even stranger idea that every possibility actually does happen, just not in this universe. This is the many worlds interpretation introduced by Hugh Everett in 1957. You're not just watching a cat in a box, you're watching the universe split. In one world, the cat survives, in another, it dies. In yet another, the vial shatters, but somehow the poison fails. You, the observer, also split, and continue to live on in each possibility, oblivious to your other selves. You wonder how many copies of you are out there drifting along branches of fate. You turn now, and the room has changed. You're standing in front of a long hallway lined with doors. Every door is a decision, a coin flip, a quantum choice. Some open to light, others to darkness. But none of them are wrong. All are real, just in separate worlds you'll never see again. But let's whisper a secret from the fringe, just between us. Some people claim they have crossed into the wrong world. The Mandela effect, a mass misremembering of facts, has been linked by fringe theorists to shifts in parallel timelines. Do you remember the Berenstain Bears, or was it Berenstein? Did Mandela die in prison or live to become president? Is it misremembering or a misalignment of memory across dimensions? Most scientists dismiss this as confabulation, the brain's tendency to rewrite and misstore facts, but the idea that multiple worlds bleed into each other, that echoes something primal. You place your hand on the cat's box again. It vibrates softly, like a drumbeat felt from far away. Is it the cat's breath? Is it the box's pulse? Or is it the sound of the universe trying to make up its mind? Somewhere in the dark you hear a gentle voice. Scientists still argue whether quantum measurement involves the observer or simply interaction with any large-scale environment. Even now, no one agrees. You drift back through time again. It's the early 20th century, and Niels Bohr and Albert Einstein are at a dinner party. Between glasses of wine and candlelight, they're arguing, not about politics or art, but about reality itself. Einstein, frowning, mutters, "God does not play dice with the universe." Bohr leans forward. "Einstein," he says, smiling faintly, "stop telling God what to do." The candle flickers. Somewhere nearby, the cat breathes, or doesn't. In recent years, experiments have tried to scale up quantum weirdness, entangling large molecules, even small diamonds, into states of superposition. But a cat, that remains metaphor, or perhaps not. There are researchers now who believe that consciousness, yours, mine, is tied deeply to quantum effects, that your thoughts may be dancing on the edge of probability, never fully collapsed. Roger Penrose and Stuart Hameroff proposed the OR theory, suggesting that consciousness arises from quantum computations in microtubules inside your neurons. It's not widely accepted, but then again, neither was quantum theory itself once. So here you lie, half asleep, half awake, suspended in your own strange superposition, the listener who listens and the dreamer who drifts. You too are Schrödinger's cat, until sleep fully claims you. But before you vanish into your own box of dreams, you hear one more whisper. We have barely begun. There's light that travels, and something else that moves even faster. There's space that bends, and shadows that outpace photons. There are paradoxes that twist motion itself into impossibility. So let the box fade now, let the cat dissolve into quiet, and follow the next anomaly, the one that travels faster than light, sort of. The box dissolves. You're no longer in a room, nor in a hallway, nor even within walls at all. You are now outside everything, outside space as you know it, floating once again through the deep velvet black, where starlight whispers and the vacuum hums with secrets. And suddenly, light appears. It slices the darkness with precision, a narrow, blinding beam. You follow it, chasing it through the void. It's fast. In fact, it's the fastest thing there is. Light, according to the sacred texts of physics, moves at 299,792,458 meters per second in a vacuum. That's not just fast, it's the limit. According to Einstein's special relativity, nothing can outrun it. Not rockets, not thought, not dreams, and certainly not you. And yet, out in the distance, something does move faster. You don't believe it at first, but there it is. A flicker, a shift, a strange shadow on a distant wall of reality. Something about it feels wrong. A point of light appears on a screen, then another, moving faster than light itself. But as you approach, the truth becomes clear. It's not an object that's moving, it's a shadow. The projection of something dancing elsewhere, its silhouette darting faster than the light that cast it. It's a trick. but not of the eye. It's a real trick, a genuine loophole in the structure of reality, because while nothing with mass can move faster than light, shadows, illusions, and entanglements, they can. This is where paradox creeps back in. Let's slow down. Breathe with me. Imagine a laser pointer. You shine it across the surface of the moon from Earth. You move your hand ever so slightly, and the red dot races across the lunar surface at a speed that technically can exceed light's limit. Why? Because that red dot is not a thing. It's not a particle. It's just the result of photons hitting a surface at different angles. No single photon ever breaks the speed limit. But the spot, the illusion, does. Now take a deep breath, because the paradox is only getting started. What if, instead of a laser pointer, you had two particles linked by something deeper than space? Something physicists call quantum entanglement. You stare at them now. They float in front of you, shimmering like beads of dew suspended in zero gravity. One is blue, one is red. You reach out, touch the blue one gently. Instantly, the red one shifts. No signal passed between them, no photon, no vibration, no wave, and yet the effect was immediate, faster than light. Einstein called this spooky action at a distance. He didn't like it, he couldn't explain it, and neither, honestly, can anyone else. Entangled particles behave as if they share information instantly, no matter how far apart they are. If you spin one, the other responds. Flip one's polarity, the other follows. The connection defies locality. It seems to exist outside space entirely. You might be tempted to think this allows for faster-than-light communication, but hold on, there's a catch. Because you don't choose the state of the first particle. It behaves randomly. Only when you compare notes, after the fact, through normal speed messages, do you see the perfect correlation. And yet, scientists still argue whether information truly passes between entangled particles or if it's merely predetermined, set in stone since the beginning of time, or maybe something else, something we don't yet understand. In 2022, an experiment called a cosmic bell test attempted to eliminate hidden variables by using starlight from opposite ends of the sky to randomize measurements. The result: entanglement holds. Reality is still weird. But let's go further. Out here in the great cosmic dark, you look toward the edge of the universe itself, and you notice something unsettling. Galaxies, billions of them, are mapped, moving away from you, and the farther they are, the faster they move. So fast, in fact, that some of them are receding faster than the speed of light. Wait, how is that possible? The answer lies not in the galaxies themselves, but in the fabric of space between them. It's stretching, inflating, swelling like a breath held too long. According to general relativity, it's not the galaxies flying through space. It's space itself expanding, carrying them along like flecks of dust in rising dough. And because relativity forbids objects from moving through space faster than light, but not space itself from stretching, the universe escapes its own limit. You realize now you're not at the center of the cosmos, but wherever you stand, it feels that way, because all around you, things move away. Every direction, every distance, every moment, further and faster. You're adrift in a bubble that refuses to behave. Remember that phrase again. Scientists still argue. Whether expansion is due to dark energy, whether space-time is flat or curved, whether the speed of light is a limit or a local suggestion. Some propose tachyons, hypothetical particles that only exist above light speed, but none have ever been seen. They remain, for now, in the realm of equations and imagination. You drift back again to Earth, hovering in the upper atmosphere, watching storms swirl below. Here, even light obeys rules, bending around the Earth, redshifting and blue-shifting in its gravitational pull. But the deeper you go, the more you see exceptions. In fiber optic cables, pulses of light can be slowed to 200,000 times slower than in vacuum. In Bose-Einstein condensates, super-chilled atomic gases, researchers have slowed light to just 17 meters per second. One team even stopped light entirely for a few moments. So light, the great constant, is negotiable. You drift through these frozen pulses, glowing like ghostly serpents in a jar. Then, suddenly, back to speed, back to the rush. It's confusing. You want rules, you crave order, but the universe whispers gently, "No, not here." Let me show you one more trick. A black hole sits before you, enormous and calm. It warps the stars around it like a lens. But near the edge, the event horizon, light cannot escape. Yet quantum physics predicts that information cannot be destroyed. So where does it go? This is the black hole information paradox, a collision between relativity and quantum mechanics. Some physicists believe Hawking radiation slowly leaks information out. Others suggest information is smeared across the horizon like a hologram. Still others believe we are fundamentally misunderstanding reality. And yes, some even suggest the entire universe might be a projection on a distant boundary, a holographic dream. But that's for another time. Now the stars slow again. The flickers of light begin to calm. Your heartbeat, soft and steady, slows to match. The universe didn't lie to you. It simply doesn't behave. Because some things can go faster than light, as long as they're not things at all. Shadows, patterns, stretching space, interlinked particles that ignore distance entirely. You close your eyes and you feel it now, a soft pulse of light just beyond your reach, chasing paradox through cosmic waters. And ahead, time bends once more. Because next we'll visit a jellyfish that never dies, and a universe that can't stop aging. You drift downward now, not falling but gliding like a petal released from time's tall tree. From the brilliance of light-speed paradoxes, you descend into warm, salt-heavy air, the soft hush of waves, and something older than all the stars you've flown past. The sea, its rhythms pulse against the edges of your hearing, steady and slow. Beneath its glassy skin, secrets wait. And among them swims a creature so peculiar, so quiet in its miracle, that it bends the very story of life and death. You follow it now, a tiny transparent bell pulsing gently in the bare, dark waters. Meet Turritopsis dawni, the so-called immortal jellyfish. It drifts past coral like a ghost with a heartbeat, unremarkable at first glance, barely 4 millimeters wide, colorless, simple. But when wounded, aged, or starving, something strange happens. Instead of dying, it reverts. It curls inward, reshapes, and transforms into its earlier polyp form. The jellyfish equivalent of rewinding into childhood. From there it grows up again, and again, and again. It does not die. It starts over. You watch this impossible cycle unfold in slow motion, like life on a loop, like time refusing to move forward. If this were just a trick of nature, a quirk of biology, it would be wondrous enough. But here's the paradox. All living things, from trees to whales to you, must obey entropy. The universe trends toward disorder. It's not just a suggestion, it's the second law of thermodynamics. Over time, things fall apart. Ice melts, metal rusts, energy spreads thin, entropy increases. This law is so foundational that many physicists believe it's the true engine behind time's arrow, the reason why the past is fixed and the future unknown. You remember the ticking clocks of Section 1. Now imagine that each tick is not just a measure of time passing, but of entropy increasing. Milk mixes into coffee. It does not unmix. You age, you do not unage. Except this jellyfish does. It sidesteps time's arrow. It glides backward on the entropy slope, not forward, and that should not be possible. Scientists still argue whether Turritopsis is truly immortal, or whether its cellular cycle merely resembles immortality. After all, it can still be eaten, crushed, infected. But the core idea stands. Some part of nature seems able to cheat the laws. You float now in warm, tropical water, following this flickering life form through coral cathedrals. The sea around you is heavy with motion. Fish dart, sediment swirls, sunlight dances in ripples. Everything moves. Forward, but turritopsis, it loops. And in doing so, it echoes something deeply unsettling to scientists, the contradiction between thermodynamic entropy and quantum mechanics. At the quantum level, particles don't care about time's direction. Their equations work just as well backward as forward. But the moment we look at the macroscopic world, your life, this ocean, the stars, time only goes one way. Why? No one knows for certain. Some claim it's just a matter of initial conditions, that the universe began in a low entropy state, and everything since has been the natural flow toward disorder. But that's not satisfying. It's like saying a story must be sad because the first sentence was too happy. Others suggest that consciousness itself plays a role, that memory and perception create our illusion of past and future, that time's flow is not fundamental but a trick of perspective. You swim deeper. Below the jellyfish, the seafloor yawns into darkness. Thermal vents hiss heat into the cold black, and you realize something else. Even here, in the darkest places on Earth, life burns. Entropy feeds the march of time, and time feeds the decay of order. But what if time isn't real? Some physicists, like Carlo Rovelli, argue that time is not a universal property of reality, but an emergent phenomenon, like temperature, like wetness, like color, useful, local, but not fundamental. The jellyfish, unconcerned, loops again. But while it dances in defiance, other things follow the rules. You drift back to shore, where a woman studies her reflection in a mirror. She traces the creases near her eyes. Each wrinkle, each breath is a victory for entropy. Inside her cells, telomeres shorten. Mitochondria falter, DNA accumulates damage. The jellyfish avoids all this somehow. Is its life less real, or has it found a secret we missed? Scientists in biotech labs now study turritopsis with reverence. If they can decode its cycle, perhaps they can slow our own. Gene therapy, cellular regeneration, artificial immortality. But here's the twist. The universe itself is not immortal. Far from it. Though it is expanding, even accelerating, it's also cooling. Energy spreads, stars die, galaxies dim. In trillions of years, black dwarfs will blink out, the last particles will decay, even black holes will evaporate in slow, lonely Hawking radiation. This is the heat death of the universe, a state of maximum entropy where no work can be done, no complexity can survive, no memory, no structure, just equilibrium. Ultimate silence. The jellyfish may loop forever, but in the end, the sea it swims in will freeze. Unless entropy is not as total as we thought. Unless there's a deeper paradox still. Some theorists now ask, could entropy itself be reversed? Are there universes, born in black holes maybe, where time runs backwards, where stars uncollapse, where death rewinds into birth? If so, would an immortal jellyfish even know the difference? You float again. The jellyfish vanishes behind coral, the sea becomes mist, and once more you rise, not upward, but outward. The arrow of time seems less certain now. Maybe it's not an arrow at all. Maybe it's a spiral or a wave or a Mobius strip. Maybe, like the jellyfish, you will return to this moment someday, in a different form, with the same curious heart. But before we loop again, we must go somewhere stranger. Inside your skull. Where you think, you decide, you act, or do you? Because next, we explore the unsettling truth that your brain may know your choices before you do. The sea recedes behind you like a breath exhaled by the cosmos. The jellyfish loops once more into the shadow of coral, and now, gently, you rise above it, through the layers of ocean and air, into the quiet press of night. You're no longer floating through galaxies or deep seas. You're hovering inside something far smaller and far more intimate, a human head, your own. The skull around. Dew pulses faintly with blood, and inside it, folds of brain matter glow softly, pink and grey, like a living nebula wrapped in bone. You descend deeper, past synapses crackling with electricity, into the warm silence of thought. And here begins the next paradox. You've always believed in your decisions. You choose, you act, you steer your life. Turn left, say yes, eat the cake. Free will, surely, it's obvious. But something is whispering now, a current beneath the surface, a delay in the ripple of choice. And when you follow that whisper, what you find is deeply, uncomfortably strange. In the 1980s, neuroscientist Benjamin Libet conducted an experiment that would unsettle philosophers and physicists alike. Subjects were asked to perform a simple task, flex a finger, whenever they felt like it. No prompting, just whenever. While they decided, Libet measured their brain activity using EEG sensors. He also asked them to note the exact moment when they consciously made the decision to move. What he discovered shook the foundations of conscious choice. The brain's readiness potential, a small, measurable buildup of neural activity, occurred before the subject reported deciding to move, sometimes by as much as half a second. In other words, your brain decides before you do. You feel that gap now as you hover among neurons. The decision forms in the back alleys of the mind like a tremor before the quake. By the time you become aware of the urge to act, the wheels are already turning. This suggests that what you think of as free will may actually be a post hoc narrative, your conscious mind catching up, rationalizing what the unconscious brain has already set in motion. You pass now between brain cells like canyon walls, where neurotransmitters leap like fireflies across synaptic gaps. The illusion of choice dances before you. A mainstream historical fact rises like a cathedral from this mystery. In the 1600s, René Descartes famously declared, "Cogito ergo sum," I think, therefore I am. But what if thinking, or at least the awareness of it, isn't the source of self at all? What if the I is just the aftershock? The paradox stretches deeper. You move forward in time, hovering now inside an fMRI lab. It's the 2000s. Researchers repeat Libet's experiment with greater precision. Machines scan subjects' brains in real time. This time, instead of just fingers, participants make binary decisions, press one of two buttons. The results are more shocking still. Scientists can predict a person's decision up to 10 seconds before they report making it. 10 seconds. Imagine it. Before you even feel the tug of choice, your brain's pattern is already visible, already predictable, a biological forecast, a neural weather report. Does this mean we have no free will? Not exactly, but the implication is haunting. Our choices may not originate in the conscious self. They arise somewhere deeper, somewhere older, somewhere not you. This is where science edges into ancient philosophy. For centuries, thinkers debated fate versus free will. From Plato to the Stoics, from Buddhist thought to Christian doctrine, the question never truly settled. But now, the battleground is neurological. You pause in the stillness of a neuron, listening. The brain is a chorus of 86 billion cells, all singing in microscopic rhythm. Most of them fire without your awareness, directing heartbeat, digestion, posture, micro-adjustments of emotion. You're a passenger in many ways, a rider atop a beast of blood and instinct. And here comes a fringe whisper. Some researchers believe the conscious mind is not a decision maker, but a storyteller, a narrator. Like the voice in your dreams, it watches what you do, guesses why, and then builds a coherent illusion of authorship. I decided to go for a walk, it says, but perhaps you didn't. You simply went, and the story came after. Still, there are pros. Tests. Some scientists argue the readiness potential isn't a decision at all, just noise or preparation. That consciousness might intervene at the last instant, like a hand on a wheel, a veto. Libet himself called this the free won't, the ability to cancel a decision in the moment. Scientists still argue whether free will is real, or whether it's an emergent trick of complexity. A beautiful illusion like colour or warmth or the sound of rain on a window. You float again, rising now into your own present-day mind. You sit at a crossroads. Should you continue listening? Should you turn off the story and sleep? What made that choice? You, your mood, a quiet firing of a network in your prefrontal cortex. Here's a quirky tidbit for your dream-bound thoughts. Octopuses have 2/3 of their neurons in their arms, not their heads. Each arm makes decisions semi-independently. Does the octopus have centralized free will or 8 conflicting ones? And what about bees? In collective behavior studies, hives seem to decide where to relocate based on thousands of tiny individual signals. No single bee knows everything, but somehow the hive chooses. Are you a hive? A parliament of neural selves? You pass now through your default mode network, the brain's idle engine, active when you're daydreaming, self-reflecting, remembering. It's active right now. Because you're not making decisions, you're drifting, and drifting feels like freedom. But underneath, always, the brain whispers, fires, decides. Even your dreams tonight will be chosen for you, by memory, by emotion, by needs you don't consciously recognize. You close your eyes inside your mind and see the gears spinning behind the curtain. A warm voice returns, the one you've been hearing since section 1. Don't be afraid, it says. Because maybe free will was never about control. Maybe it was about awareness, to be awake inside the pattern, to know the story even if you're not the author. And with that thought, you feel yourself tilt forward again. Motion. Because next, we will step inside a paradox that lives not in the brain, but in the body, in every footfall, every gesture, every journey, the puzzle of motion itself, and the race that never ends. You open your eyes to a road. It stretches ahead, smooth and silent, through a landscape blurred by morning mist. On this road, you stand at the ready, and beside you, preparing to run, is a tortoise, old, steady, shell shining faintly with dew. A moment later, an arrow rests beside your foot. It's notched into an invisible bow, its tip poised in timeless suspension. Behind you now, a voice calls out, not from a person, but from paradox itself. It says, "You will never catch the tortoise." And the arrow? It will never move. Welcome to the ancient mind trap known as Zeno's paradoxes. Puzzles so enduring they've rippled through millennia of thought, from Greek amphitheaters to modern physics labs, teasing the limits of logic and the very notion of motion. Let's begin with the most famous, Achilles and the tortoise. The Greek hero. Achilles challenges a tortoise to a race. Confident in his speed, he allows the tortoise a small head start. Once the race begins, Achilles sprints forward. But before he can reach the point where the tortoise began, the tortoise, slow but steady, has moved slightly farther ahead. Achilles reaches that new spot, only to find the tortoise has moved yet again. This continues forever. Every time Achilles arrives at where the tortoise was, the tortoise is somewhere else. The distance shrinks, yes, but it never vanishes. The race is never truly over. According to Zeno, Achilles never wins. But you've watched races, you've run them. Of course, Achilles overtakes the tortoise. So what's going on? Zeno wasn't trying to trick you. He was demonstrating something profound about infinity, how an infinite number of steps can occupy a finite space or time. This paradox hinges on dividing space into infinitely smaller segments. If time and motion are continuous, infinitely divisible, then motion must consist of infinite steps. And in that infinity, forward progress becomes an illusion. You feel it now, walking down this misty road. Each step you take could be divided into halves, and those halves into quarters, and so on, endlessly. Between every 2 points, there is another point. So how do you ever get anywhere? Mathematically, we resolve this today using converging series. The distance Achilles must cover shrinks with each step, half the remaining length, then half of that, and so on. These diminishing steps form a geometric series that adds up to a finite total. Achilles does catch the tortoise because the infinite sum converges. But the feeling of the paradox lingers, because motion, at its core, still doesn't behave as cleanly as we'd like. You step again, and now find yourself beside the second of Zeno's traps, the arrow paradox. In it, you examine an arrow in flight. But at any single instant, any frozen slice of time, the arrow occupies one position. It isn't moving in that instant. And if time is made of such instants, motionless snapshots, then when exactly is the arrow moving? If each moment contains no motion, how does motion emerge from stacking them? The arrow hangs beside you now, suspended in time like a comma waiting for the next word. It does not tremble. It does not shift. And yet, you know it flies. You've seen arrows soar. The contradiction lies in our discrete thinking, dividing time into instants as if the flow of motion were a flipbook made of frozen pages. But motion, it seems, isn't in the frames, it's in the transition. Today's physics defines motion through calculus, by the concept of limits and derivatives. Velocity is the instantaneous rate of change. It doesn't live inside a single moment, but in the neighborhood around it. Still, calculus offers answers, but not always understanding. And modern physics has its own troubles with motion. Let's enter the realm of Planck units, the smallest possible scales of space and time. At these levels, around 10^35 tonnes, 135 meters, and 10^44 seconds, 44 in 44 seconds, space-time may not be continuous at all. It might be quantized, like pixels on a screen or grains in sand. You cannot go smaller. If that's true, then Zeno's paradoxes dissolve. Motion cannot be infinitely divided. It comes in indivisible chunks. Achilles overtakes the tortoise not by slicing the road thinner and thinner, but by leaping from one granular point in space-time to the next. But even here, at the frontier of theoretical physics, uncertainty persists. Scientists still argue whether time and space are continuous or discrete, a smooth river or a cosmic grid. And in some interpretations of quantum gravity, even the concept of motion becomes fuzzy. Particles don't follow clear paths. They drift through probability clouds. The arrow doesn't fly. It smears, becoming a blur of possibility. A quirky gem from the ancient world adds to the riddle. The philosopher Heraclitus once said, "You cannot step into the same river twice, because both you and the river are always changing." Zeno might reply, "You cannot even step once because motion itself is an illusion." You smile now, caught between these voices, walking through a world that seems to move, and yet hides infinite stillness within. Even in your own body, motion deceives. Atoms never touch. Your hand does not truly press against your arm. The electrons in both repel each other, bound by quantum forces. Touch is the illusion of contact. Motion is the illusion of flow. And yet here you are, moving forward in this story, sentence to sentence, scene to scene. How does anything move at all? In biology, motor proteins like kinesin walk along microtubules in your cells, carrying cargo like little mechanical workers. Step by step they move, but zoom in close enough and they don't walk. They stochastically tumble, nudged by thermal vibrations and chemical reactions. Randomness guides them, not will. Even the smallest motions in your body are more chaos than choreography. And still, you move. Motion exists even if it hides behind paradox. Zeno's puzzles don't prevent movement. They remind us how strange it is that we move at all. The road beneath you fades now. The tortoise vanishes into mist. The arrow continues on its path, caught forever between moments. And you drift onward, gliding from the realm of movement into one of mass and gravity, where something enormous waits, something that bends not just motion but reality itself, a whole with weight and somehow with nothing inside. Next, we fall into the dark paradox of black holes, objects that weigh everything and yet, impossibly, radiate nothing but secrets. You feel it before you see it. A shift. As if something in the space around you clenched, pulling all light, all sound, all reason inward. The stars go thin, stretched like taffy. And then, at the edge of everything, you see it, a circle of darkness, perfect. silent. Not a hole in space, but a hole in knowing. You are gazing upon a black hole, that monstrous offspring of gravity and paradox, a region so dense, so heavy that not even light can escape, a place where time warps, space folds, and logic shivers. And here's the most impossible thing: it isn't empty. It's full of nothing. You drift closer, and the universe starts to distort. Behind you, the stars are brighter. Ahead of you, they vanish. Black holes are born when massive stars collapse at the end of their lives. Their core, crushed under its own weight, implodes. And in that moment, a boundary forms, the event horizon. Anything that crosses it, light, matter, dreams, can never return. To an outside observer, you slow as why. Fall in, slower, slower, until your motion seems to freeze at the edge, but to you, inside, you fall freely, endlessly into the singularity. Now pause. Let's reach gently toward the heart of the paradox. At the center of a black hole lies a singularity, a point of infinite density and zero volume. A place where gravity becomes so intense that the laws of physics break down. Space and time themselves curl into a single point. It is not just a mystery, it is a failure of knowledge. General relativity, Einstein's great gift, predicts this singularity. But at this scale, quantum mechanics must apply. And yet, quantum theory cannot describe it. We are left with two great frameworks, one for the large, one for the small. And they refuse to speak to each other inside the black hole. This is where physics eats itself. Now consider the information paradox. In quantum mechanics, information is sacred. It cannot be destroyed, not even by time. Every particle's identity, its spin, its history must be preserved. Even if particles merge or decay, the information lingers somewhere. But black holes swallow information. Throw a book into a fire, and its molecules scatter, but the information persists in heat, smoke, ash. Throw a book into a black hole, and it's gone. Truly gone. That breaks the rules. Stephen Hawking in the 1970s proposed that black holes radiate energy, now known as Hawking radiation. It's a quantum effect at the edge of the event horizon where particle-antiparticle pairs form from vacuum. One falls in, the other escapes. The result? Black holes can evaporate. Over unimaginable timescales, they lose mass until, poof, they disappear. But if the black hole vanishes, and the information was inside it, where did it go? That's the information paradox, and it has haunted physicists for decades. Scientists still argue whether information escapes in the radiation, or gets smeared on the surface of the horizon, or perhaps encoded in subtle fluctuations. Some suggest that black holes store information in a holographic shell, a skin of knowledge on the event horizon itself. This is the holographic principle, and it whispers something profound, that maybe our universe isn't three-dimensional at all. Maybe it's a projection. You float closer to the event horizon, time slows, your thoughts stretch into syrup, and still you drift forward. Here's a quirky twist from modern theoretical physics. If you fell into a large enough black hole, you wouldn't even feel the horizon. No crunch, no flash, you'd pass through it unaware until, eventually, you reached the singularity, and everything ended. But from the outside, you'd appear frozen, fading, smeared into photons, never quite crossing. Two perspectives, one death, both real. What's more, black holes aren't rare, they pepper our galaxy. At the center of the Milky Way, in the heart of a luminous storm, lies Sagittarius A, a supermassive black hole with 4 million times the mass of the Sun. And across the observable universe, it's estimated that there may be 100 billion black holes or more. They eat stars, they merge, they spin, and in 2019, for the first time, we saw one, or rather, its shadow. The Event Horizon Telescope, a network of observatories spanning the globe, captured the outline of a black hole in galaxy M87. A fiery ring framing perfect darkness. That image, pixelated and ghostly, is humanity's first portrait of paradox made visible. Still, the questions multiply. Do black holes truly evaporate? Could the universe itself be the inside of a black hole? Some physicists toy with the idea that black holes spawn baby universes, whole realms budding from singularities, expanding inward as we collapse outward. Others dream bigger still. What if our universe is a hologram on the event horizon of a higher dimensional black hole? You drift upward now, passing strange geometries, warped grids of space-time, stretched like webs around the singularity. Time is meaningless here. Left and right melt into each other. All directions lead inward, and at the edge you see a memory. You sitting in your chair, your hands curled beneath your cheek, your breath slowing, listening to this story. How did you get here? You remember footsteps, you remember a jellyfish, you remember arrows and tortoises and a cat in a box. Now you are near the truth, that all of it is part of a system that does not behave the way it should. Mass can vanish, light can bend, information can burn, and nothing, not even time, is immune to the whole's quiet hunger. You drift away from the singularity now, slowly reversing the fall, as if entropy itself allowed a single exception. But before you leave, you sense another impossibility. Something else inside the black hole, calling out. Because next we'll step beyond the event horizon, not physically but mathematically, and explore a space where particles borrow energy from the vacuum, where something comes from nothing, and where emptiness is not truly empty. You rise now from the well of the black hole, slowly, delicately, as if the universe itself is letting you go. The light returns, faint at first, like morning seen through gauze. Your body, or what's left of your shape, reforms gently as you ascend through thought, through theory, through time. And what greets you next is nothing. So it seems. You're standing now in what appears to be empty space, the great void between galaxies. There are no stars here, no planets, no roaring suns, just silence. But listen closely. The vacuum hums, not with sound, but with something deeper, something stranger, something vibrating beneath reality's skin. You have entered the paradox of vacuum energy, the mystery of how nothing is not truly nothing at all. Let's begin with what science used to think. For centuries, philosophers and scientists alike believed in the concept of a true vacuum, a perfect void, an absolute emptiness, the absence of all matter, all energy, all movement, a blank stage on which the universe could perform. But quantum physics changed the script. In the quantum realm, uncertainty is law. The more precisely you know a particle's position, the less you can know its momentum. The more tightly you constrain the energy of a region, the fuzzier its time. And so, even in empty space, even in the vacuum, fluctuations must occur. Particles and antiparticles pop into existence briefly, borrowing energy from nowhere, and then annihilate each other before reality notices. These are virtual particles, and they swarm the vacuum like ghosts at a masquerade. They are not detected directly, but their effects are real. Here's a quiet marvel. In the 1940s, physicists Casimir and Polder predicted that two uncharged metal plates, placed extremely close together in a vacuum, would experience a tiny force pulling them together. Why? Because between the plates, some quantum wavelengths are excluded. There's slightly less vacuum energy there than in the space around them. And sure enough, when tested, the plates moved. The effect was real. The Casimir effect had spoken. Even nothing is something. This leads us to one of the most vexing paradoxes in physics, the vacuum catastrophe. Quantum field theory predicts the amount of energy in empty space. When you calculate the expected vacuum energy based on known particles and forces, the result is enormous. a number so absurdly large that if it were accurate, the universe would have torn itself apart in its infancy. Yet here we are, stable, unripped. The actual observed vacuum energy, what we call the cosmological constant, is 120 orders of magnitude smaller than the prediction. That's a 1 followed by 120 zeros. It is, perhaps, the most inaccurate prediction in the history of science. Scientists still argue whether this discrepancy is a clue or a catastrophe, whether there's some deep cancellation at play, some hidden symmetry that wipes the energy clean, or whether we are misunderstanding vacuum itself. You float now in this not-so-empty void, and you feel the pull of virtual particles brushing past your skin. They are everywhere, popping into and out of existence in less than a billionth of a second. And then you realize something astonishing. These fluctuations may be the very thing responsible for gravity itself. Some theories, like emergent gravity, suggest that gravity is not a fundamental force but a side effect, an emergent property of underlying quantum processes in the vacuum, like temperature from molecules, like motion from Zeno's paradoxes. If this is true, then black holes, dark energy, and even space itself may be products of a holographic information field, with your entire experience arising from patterns on the edge of reality. This is not a metaphor, it is the actual mathematics of certain string theories. And it echoes an ancient truth: what appears empty is rich. A quirky tidbit to tuck into your dreams: the Lamb shift, discovered in hydrogen atoms, arises due to virtual particles tweaking electron energy levels. It's a real, measurable change, caused by the presence of nothing. So, even the structure of atoms depends on the dance of ghosts in the void. Now, peer closer. The vacuum is not flat, it seethes with potential. In some early universe models, it is like a bowl, the universe at first perched on a ledge of false vacuum until a quantum nudge sent it rolling into a more stable state. That nudge, the Big Bang. But here's the unsettling twist. What if we are still in a false vacuum? What if this peaceful state is just a precarious plateau, and someday a fluctuation will tip us into a new vacuum, destroying everything in an instant? This is called vacuum decay. No warning, no explosion, just a bubble of new physics expanding at light speed, rewriting reality as it passes. Don't worry, it probably won't happen for trillions of years, probably. You reach out now and touch the vacuum itself. It ripples, not with matter but with fields, quantum fields that stretch across all of space. In modern physics, particles are not the building blocks of reality, fields are. Each type of particle, electron, quark, photon, is a ripple in its respective field. Even the vacuum is a seething sea of potential, alive with the quiet storm of unseen waves. And just as particles arise from fields, perhaps you arise from something deeper still. Your thoughts, your choices, your dreams. Ripples in a field of consciousness, emerging from the strange substrate of a quantum vacuum. There is one last elegant paradox to consider. The vacuum, this shimmering nothingness, is the default state of the universe. It is all-encompassing, omnipresent. Yet, it's also the most active thing in physics. How can the most passive concept, emptiness, be the most dynamic, the most powerful? Because paradox is not a flaw in the universe. It is its foundation. And now, as the vacuum stirs around you, it carries you forward once more. Not to a distant galaxy or a forgotten sea, but to the simplest place of all, a room with a slit and a particle. Next, we step into the laboratory of shadows, where light forgets how to behave and observation itself rewrites reality. The double-slit experiment awaits. You find yourself standing now in a room so still, so exact, that it might as well be the inside of an idea. Smooth white walls, no windows, no clocks, just a long black table stretching in front of you, and at its far end, two narrow vertical slits cut into a panel of metal. A single photon rests in a chamber behind you, like a breath held in the dark. This is the double slit experiment, a chamber of riddles where the rules of nature twist like smoke, and where light forgets what it is. You are here to witness a paradox that has haunted physicists since the dawn of the quantum age, a paradox that calls into question the meaning of reality, of observation, and perhaps even of you. It begins simply. Imagine you fire a stream of particles, say grains of sand, at the panel with two slits. Behind the slits is a screen that records where each grain lands. What would you expect to see? Two lines, right? Two clusters directly behind the slits. Now imagine you switch to waves, ripples on a pond perhaps. As the waves pass through both slits, they spread, overlap, interfere. Peaks meet peaks, valleys meet valleys, and the pattern on the screen becomes a series of stripes, bright where waves reinforce, dark where they cancel. Simple. But now we do it with light. Individual photons, one at a time. Not a wave, not a beam, just a single particle. You fire a photon. It hits the screen, you fire another, then another. Over minutes, hours, days, the pattern builds. And what do you see? Not two neat lines, but interference stripes, as if each photon has gone through both slits, interfered with itself, and landed accordingly. Each particle behaves as if it's a wave that travels all possible paths simultaneously, until it hits the screen and chooses one. This is the birth of quantum superposition, the idea that particles exist in all states at once until observed. Now comes the twist. You place a detector at the slits, just to check. You want to know which slit each photon goes through. And suddenly, the pattern vanishes. No more stripes, just two clumps. Your act of observing has changed the outcome. By knowing which path the photon took, you've forced it to decide, to behave like a particle, not a wave, and the interference disappears. Reality, it seems, does not exist in a fixed state. It waits for you to look. You walk now through this impossible room, the slits looming on the wall like twin doors to another kind of physics. And here's the deeper paradox. The measuring device doesn't even need to touch the photon. Just having the possibility of obtaining information is enough to change the result. As if the photon can sense your intent. Scientists still argue whether the wave function, the mathematical object that describes a particle's probabilities, is a real thing or just a tool. Is the particle truly in all states at once, or do we simply not know and the wave function reflects our ignorance? In the Copenhagen interpretation, the wave function collapses when observed, but in the many worlds interpretation, it doesn't collapse at all. Instead, the universe splits. In one world, the photon goes left. In another, it goes right. Infinite paths, infinite use. And here's the eerie part. It doesn't stop at photons, electrons, molecules. Even atoms exhibit the same interference patterns. And in theory, larger objects, even you, if isolated enough, could also exist in superposition. But there's a catch. Larger systems decohere quickly. They interact with their environment, and their delicate quantum states collapse into classical ones. The cat in the box? Alive or dead, once you peek. Still, a shadow remains, a whisper that says, reality does not behave until watched. A quirky note floats into your mind, gentle and strange. In 2015, scientists at the University of Vienna performed a delayed choice experiment with entangled photons. They decided after a photon passed the slits whether or not to observe it, and the pattern still changed. As if the photon's past behavior was altered by a future decision. You pause now and wonder, does the universe contain time at all? Or is it made of choices, layered atop each other like folded paper? Your feet step forward and you're no longer in the lab. You're inside the photon. You spread in every direction, through both slits, through none, along paths that spiral around stars and duck beneath oceans. You are probability, you are possibility. But a single measurement collapses you into a point. from wave to dot, from maybe to this. And now you are a person again, watching, thinking, choosing. Does this mean your consciousness shapes the universe? Some scientists explore the observer effect and its relation to conscious awareness, though mainstream physics stops short of saying your mind causes collapse. Still, others, fringe voices on the edge of cosmology, wonder aloud. If the universe requires observation to resolve into form, then does it imply a cosmic observer, or that we ourselves are the mirror in which the cosmos sees itself? You look at your hands. Are they waves, collapsed into flesh only when you glance down? Is this story a waveform collapsing with each word you hear? The philosopher Eugene Wigner once asked, "It is not possible to formulate the laws of quantum mechanics in a fully consistent way without reference to consciousness. But no one can say what that truly means. What is consciousness? What is observation? These are the next paradoxes, shimmering in the distance like heat on a road. But for now, let's stay here, in this impossible room where two slits reveal the wild truth that particles can act like waves, waves can act like particles, and reality adapts to attention. This much we know: the world is not made of things. It is made of interactions, of verbs, not nouns, of processes, not pieces. Nothing is fixed until it is measured. Nothing is certain until it is seen. And still, somehow, you exist. Next, we will step back into your body, into the engine that powers all thought, the brain. But this time, not to question free will, but to wonder at something stranger still. Why do you dream? And what is it exactly that dreams you? You're floating again, this time not through cosmic voids or atomic shadows, but through a warm and personal twilight. The sensation is familiar. You've been here before. This is the edge of sleep, somewhere between waking and drifting, where thoughts loosen their grip and the world begins to dissolve. Here, the boundary between real and imagined blur is like ink in water. Welcome to the paradox of dreaming, where your mind constructs entire worlds while the body lies motionless, paralyzed by sleep. And somehow, none of it feels like fiction until you wake. The question drifts toward you like fog. If you're unconscious, how is your brain so vividly conscious? Let's begin with what sleep scientists know. Every night, your brain cycles through stages N1, N2, N3, and REM. The first three, non-REM sleep, are increasingly deep. Your muscles relax, heart rate slows, brainwaves stretch into delta rhythms, deep and slow. But then, after about 90 minutes, something strange happens. Your eyes begin to twitch under their lids, your heart rate quickens, and inside your skull, the brain lights up, almost as if you're awake again. This is REM sleep, rapid eye movement, and this is where most dreams take place. During REM, your motor neurons are actively inhibited. The body becomes effectively paralyzed. You can't act out your dreams, but your brain, it surges. The visual cortex activates. So does the amygdala, your emotional center. The default mode network hums like it does during daydreaming. You are seeing, feeling, remembering, and yet you are asleep. The paradox thickens. How can such a vivid mental cinema play out inside a state of unconsciousness? Some theories propose that dreaming is the mind's rehearsal space. Simulations that help you process trauma, rehearse danger, test decisions. Others think dreams are just noise, your brain's attempt to make narrative out of chaotic firing. But neither answer satisfies. Because here's the thing, dreams feel real. Not just in how they look or sound, but in how they mean. You feel joy, terror, guilt, curiosity. Sometimes those feelings linger after waking, sometimes they change how you live. How can something so intangible leave such a deep footprint? You pass now through the limbic stem, the emotional furnace of your brain. During REM, it blazes with activity. That's why dreams can feel more intense than real life, more vivid, more raw. You dream of losing your teeth and wake trembling. You fly over oceans and carry that freedom into your morning. Even animals dream. Dogs twitch their paws. Octopuses change colors while asleep. Rats, when studied, replay mazes in their dreams, neurons firing in the same sequence they used while awake. Dreams, it seems, encode experience. But what if dreams are not just reflections? What if they are blueprints, ways the brain builds the self? Consider this. Babies spend up to 50% of their sleep in REM. Their developing brains are flooded nightly with patterns of light, sound, sensation, not as memories, but as prototypes. The infant brain may be training itself through dreams before it even knows the world. Now for a historical flash. In 1899, Sigmund Freud published The Interpretation of Dreams, arguing that dreams were windows into the unconscious. Desires, he said, repressed in waking life, found shape in the symbolic landscapes of dreams. Today, neuroscience has complicated Freud's picture, but the mystery remains. Whether you see dreams as suppressed urges or stochastic rehearsals, they remain uncannily meaningful. You dream of a hallway that leads nowhere, of someone calling your name through water, of falling, of flying. What decides the script? Here's a quirky scientific tidbit. Lucid dreaming, where you become aware you're dreaming, can sometimes be induced by external cues like flashing lights or sounds timed to REM sleep. In a 2012 study, lucid dreamers were even able to signal researchers from inside their dreams using pre-arranged eye movements. That's right, communication from inside a dream. As if part of you is still here, narrating, while another part is inside the story, flying, swimming, falling in love with a stranger who might be yourself. And yet, another paradox yawns before you. You spend a third of your life asleep, years of dreams. Why don't you remember most of them? The hippocampus, your brain's memory hub, is relatively quiet during REM. Scientists still argue whether this is a bug or a feature. Some think dreams are too chaotic to store. Others propose that dream forgetting protects waking memory, that if you remembered everything, your real-life memories would drown. Still, some dreams remain, sometimes for decades, and in them, strange rules emerge. People you've never met, but somehow know. Buildings that go on forever. Events that feel prophetic, or so impossibly emotional they reshape how you see someone in waking life. But are these dreams you? You remember earlier, the conscious self is a narrator, a storyteller, not always the originator. So who dreams? One theory, the activation synthesis hypothesis, suggests that dreams arise from the brainstem firing random signals, which the cortex then weaves into a story. Another theory, predictive coding, flips it. Your brain, it says, is always predicting, constantly updating a model of reality. Dreams, then, may be offline simulations, where your brain tests and refines that model in a sandbox of sleep. Both suggest the same eerie conclusion. The dreamer is not a single voice. It is a choir of processes, emotion, memory, sensation, woven together so seamlessly you mistake it for self. And sometimes, even in waking life, the dream never ends. Consider hypnagogia, the transitional state between wakefulness and sleep. In those moments you hear voices, you see impossible images, you solve problems you couldn't during the day. Thomas Edison used to nap with steel balls in his hands. When he slipped into dream state, he'd drop them, waking up just in time to catch the insight before it vanished. Salvador Dali did the same. Even mathematical breakthroughs have emerged from dreams. The chemist Kekulé dreamed of a snake biting its tail and realized the structure of the benzene ring. The dreaming brain, in other words, thinks differently. It makes connections the waking mind would never dare. Maybe this is the true paradox. You dream most clearly when your self is most absent, when you've let go, when the reins have passed to a deeper system, one that doesn't speak in words, but in symbols, in doors and oceans and hands reaching through fog. And when you wake, the dream dissolves, except when it doesn't. Because next, we're going to peer into a different kind of paradox, one rooted not in sleep, but in life itself. where memories vanish before they even form, where minds fracture without warning, where a person standing before you can recall the past with vivid clarity while forgetting the sentence they just spoke. The paradox of memory awaits. The room dims now, softening into sepia tones as though the very walls remember. A photo album opens in your mind, pages flutter, snapshots appear. Your first bicycle, the smell of your grandmother's kitchen, the time you forgot why you entered a room. You are standing inside your own memory, but not just a memory, a paradox. Because even as you recall your life piece by precious piece, science tells us this. Memory is not a recording, it's a reconstruction. Every time you remember something, you change it. Let's begin with a simple idea. That memory is like a video archive, reliable, consistent, tucked away in the vault of the mind, waiting to be played. But that's not how the brain works. When you recall a memory, your neurons refire in the pattern that originally formed it. But the firing isn't perfect. The context is different. Your mood, your age, your body, all have shifted. And so the memory is edited, updated. Each remembering becomes a rewriting. You're not retrieving the past, you're remaking it in the present. This is the paradox of reconstructive memory. The hippocampus, the seahorse-shaped structure deep in your brain, plays a central role here. It doesn't store memories like books on a shelf. It binds together fragments. TS, emotion from the amygdala, visuals from the occipital lobe, sounds from the auditory cortex. It's a storyteller, not a librarian. And the story, never quite the same twice. That's why eyewitness testimony, long considered gold in courts of law, is now seen as dangerously unreliable. People confidently recall faces, colors, timelines, and yet countless studies show how easily manipulated memory is. Change a single word in a question. Did you see the broken headlight? Versus, did you see a broken headlight? And you alter what the person remembers. This is known as the misinformation effect. The memory updates itself to fit the question, to fit the moment. And now consider this strange and sorrowful paradox. What if memory becomes too stable, too persistent? In post-traumatic stress disorder, PTSD, a traumatic event imprints so deeply that it cannot be reshaped. It intrudes, it burns. The memory feels as real as the day it happened, with no softening from time. The brain's plasticity, normally a gift, fails to rewrite the pain. Scientists still argue whether reactivating traumatic memories during therapy, then overwriting them with new emotional context, can truly reduce their power. It's a controversial practice known as memory reconsolidation, but at the other extreme lies a gentler horror, anterograde amnesia, the inability to form new memories. You meet someone, you talk, you smile. They turn away for a moment, and when they look back at you, it's as if you've vanished. This is the condition made famous by the real-life case of Henry Molaison, or HM, a man who had parts of his hippocampus removed to treat epilepsy. The seizures stopped, but so did his ability to form new long-term memories. He lived in a perpetual now. He could carry on a conversation but forget it minutes later. He could learn a skill, like tracing a star in a mirror, but have no recollection of practicing it. This is the paradox. His procedural memory still worked, but his declarative memory, the remembering of facts and experiences, had vanished. Different kinds of memory, different systems, each with their own fragile roots in the brain. And that brings us to working memory, the system that holds information briefly in your mind while you use it, like repeating a phone number or remembering where you parked. It's not storage, it's active space. But here's a quirky fact. Working memory has a strict capacity. You can typically hold about 7+2 chunks of information at once. This limit, first proposed in 1956 by psychologist George Miller, is often called the magical number 7. Yet modern neuroscience suggests this number may be lower, closer to 4, depending on how complex the chunks are. Now pause. What are you remembering right now? The last sentence? A feeling from earlier today? The face of someone you love? How do these things remain in your mind when the brain is constantly replacing cells, rewiring pathways, recycling proteins? Some researchers believe memories are encoded not in fixed spots, but in patterns of connectivity, dynamic networks that persist through constant change. In this way, your identity, yourself, is a story told by a shifting chorus of neurons, and every time you recall it, you reinforce it. You become it again. But here's another paradox to hold close. Some of your most defining memories may be false. Studies have shown that people can be led to remember entire events that never happened. Going to Disneyland and meeting Bugs Bunny, for instance, which is impossible since Bugs isn't a Disney character. Once planted, the false memory feels real, vivid, emotional, untouchable. The same hippocampus, the same cortex, the same neural pathways light up. Truth in memory is slippery. You may now recall that time you solved a riddle alone, but actually someone whispered the answer, or the conversation you're sure happened in summer, but took place in the cold of jars. Newery. Memories are not snapshots, they are impressions, guided by mood, coloured by belief, malleable, fragile, precious. And yet they make up the only map you have of your life. You step forward into a chamber filled with fragments, flickers of days long past. You see your first teacher's handwriting, the way your fingers trembled before your first kiss, the strange warmth of crying with laughter, and you realize you don't just remember events, you remember feelings. Emotion, not detail, is the glue of memory. That's why you forget the plot of a movie, but remember how it made you feel. Why you forget what someone said, but never forget how their words landed. In this way, perhaps memory is not about preserving the past, but about guiding the future, about helping you know who to trust, what to fear, what to love. And that brings us gently to a final mystery. If memory is so mutable, so slippery, how does anything stay the same? The answer is waiting in the code of life itself, in the molecule that records not memory but inheritance. Next, we will descend into the spiral stairwell of your cells, to the double helix of DNA and the paradox of how stability survives in a world built on change. You descend now, not through space or time, but through scale, past neurons, past cells, past organelles and membranes, into the very code of you. It waits in the quiet, coiled and precise inside nearly every cell you've ever had. The double helix, DNA. 4 letters, A, T, C, G, repeating, twisting, instructing. A ribbon of language that tells your body how to build itself over and over, day after day. And yet here too, in this elegant spiral, a paradox unfurls. Because DNA is both stable and unstable, both incredibly robust and eerily fragile, it records the instructions for life itself and yet changes in the tiniest ways that can echo for generations. You are reading a text that is older than language, older than thought, and yet it's still being written. Let's begin with what DNA is supposed to do. It holds the blueprint for all living things. The bases, adenine, A thymine, T cytosine, C and guanine, G, pair off across a ladder-like structure, forming genes. Each gene is a sentence. Together, they make the book of you. These genes code for proteins, the building blocks and workers of your body. Muscles, enzymes, hormones, all crafted from the instructions in your DNA. But the real marvel is replication. Your cells divide constantly, and before they do, your DNA must be copied, accurately, precisely, every letter in order. Your body does this millions of times a second across trillions of cells, and yet mistakes happen, tiny errors, a letter swapped, a loop skipped. These are mutations. Most are harmless, some are even helpful, the raw material of evolution. Others can be catastrophic. This is the first paradox. Life depends on both fidelity and error. Too few mutations and evolution stops. Too many and organisms fall apart. Your very existence is a delicate balance between perfect copying and creative failure. Here's a strange twist. Your DNA is constantly under attack. From ultraviolet rays, from reactive oxygen species, from copying errors. Each cell in your body experiences an estimated 10,000 DNA lesions per day. And yet, you persist. Your cells deploy repair enzymes, molecular medics that patrol your genome, correcting breaks, patches, mismatches. Like librarians restoring ancient scrolls, they preserve the text, mostly. But sometimes a change slips through, and if it occurs in the right place and is passed to your children, it becomes a heritable trait. In this way, your body carries not just yourself, but the echoes of ancestors, changes made thousands, even millions of years ago. Freckles, eye color, lactose tolerance, all written in this ancient scroll. And here's the next paradox. While the code is fixed at birth, its expression is nous. And this is the science of epigenetics, where genes are switched on and off by chemical tags, environmental cues, stress, diet, even trauma. You can have a gene for high intelligence, or for depression, or for muscular strength. But if it's turned off, it's as though it doesn't exist. And those switches, some of them are inherited too. Trauma experienced by a grandparent may echo in a grandchild's stress response, not in the letters of DNA, but in the methyl groups and histones that wrap it. So the paradox deepens. Your DNA is yours, but its behavior is shaped by lives you've never lived. You are not just a descendant, you are an accumulation. And sometimes what gets passed down is more than biology. A quirky detail: jellyfish of the species Turritopsis dawni can reverse their aging process, reverting from adult back to polyp form over and over. They are, in a sense, biologically immortal. What's written in their DNA allows them to defy what we consider inevitable. And yet, in humans, aging marches forward, not because DNA is running out, but because its maintenance begins to fail. Telomeres, the protective caps at the ends of chromosomes, shorten with each replication. Eventually the cell stops dividing, it goes quiet, or worse, it malfunctions. And so we age. But even that process is being questioned. Scientists still argue whether aging is a byproduct of wear and tear, or a programmed process encoded into DNA itself. If it is the latter, if aging is part of the blueprint, then could we edit the code? That brings us to the dazzling promise and dark temptation of genetic engineering. With tools like CRISPR-Cas9, we now have the ability to precisely edit genes, to snip out mutations, to insert new instructions, to rewrite parts of what makes you, you. Already, this has been used to treat genetic blindness, blood disorders, certain cancers, but it raises haunting questions. If we can alter the code of life, where do we draw the line? Correcting disease is one thing, but what about enhancement, intelligence, strength, memory, appearance? And once those changes are made in embryos, they become heritable. We would not just be altering ourselves, we would be shaping the future of our species. A child born with edited genes will live inside a story they never chose, a story that rewrites itself with every generation. In this way, the double helix is both a ladder and a mirror. It climbs into the past and reflects what you are, but it also points forward, twisting toward futures we can barely imagine. And despite its elegance, DNA holds mysteries still unsolved. Over 98% of the human genome does not code for proteins. For decades it was dismissed as junk DNA, but now we know much of it plays regulatory roles, controlling when and how genes are expressed. And still, huge regions remain enigmatic. What is their purpose? Are they ancient codes from ancestors long extinct, or remnants of forgotten experiments in evolution? You float through the spiral stairwell of the genome, surrounded by whispering strands of code, each one a possibility, each one a record, each one a contradiction. Because the final paradox of DNA may be this: it is the most stable molecule known, able to survive for tens of thousands of years as found in fossils and frozen mammoths. But it is also the most dynamic, reacting to environment, rewriting itself, vulnerable to mutation and influence. It is who you are. But it is also not enough to explain who you are. Not your dreams, not your values, not your deepest loves or loneliest thoughts. Just a framework, a foundation. The rest is interpretation. And that brings us to our next step, one where biology, memory, and thought converge in a final enigma. Consciousness. Not what you remember, not what you dream, but the awareness that you are remembering, that you are dreaming. A paradox wrapped in self. You arrive now at a strange stillness, not the quiet of space, nor the hush of memory, but a deeper kind of silence. The kind that waits behind your every thought. It's always been there, even before you noticed it. This is the seat of self-awareness, the watcher behind the eyes, the one who knows you are here. You have arrived at the most bewildering paradox of all, consciousness. The question that echoes across centuries: how does matter, inert, predictable atoms, give rise to experience? A neuron is just a cell, a protein is just a chemical, a synapse is just a connection. And yet, when arranged in the right way, they produce color, fear, imagination, the scent of rain on warm pavement, the ache of a goodbye. How? This is the hard problem of consciousness, a term coined by philosopher David Chalmers. The easy problems, how we process stimuli, how we form memories, how we move our limbs, are challenging, yes, but they deal with functions. The hard problem asks, why does it feel like anything at all to be you? You close your eyes, the world vanishes, but you remain, not as a name or a face or a job, but as awareness itself. And here the paradox begins to pulse. You are your brain, but your brain cannot fully explain you. Let's look at what science knows. Consciousness seems to arise from complex networks in the brain, especially in the cerebral cortex, thalamus, and reticular formation. These regions form feedback loops, circuits that not only process information, but process the processing. In this recursive architecture, thought bends back on itself, a brain that not only sees, but knows that it sees. This is metacognition, thinking about thinking. And it's not uniquely human. Elephants recognize themselves in mirrors. So do magpies, dolphins, great apes. Some parrots appear to understand context and deception. Cephalopods, octopuses specifically, exhibit behavior so complex that scientists still struggle to understand, and how their radically different nervous systems produce something so uncannily aware. So consciousness, whatever it is, may not be binary, not off or on, but a spectrum, a gradient of awareness from simple reactivity to full-blown introspection. Still, no one can say where the line is drawn, or if there is a line at all. Scientists still argue whether consciousness is an emergent property, something that arises automatically when a system becomes sufficiently complex, or whether it is something more fundamental, baked into the universe itself. This latter idea leads to panpsychism, the proposal that all matter has some rudimentary form of experience, that the building blocks of the cosmos are not just mass and charge, but awareness. To some, this sounds like poetry, to others, heresy, and yet, it's one of the few theories that tries to explain how subjective experience arises from objective matter. And here's a quirky twist. Some scientists are trying to measure consciousness. The Integrated Information Theory, IET, proposes that the more interwoven and irreducible a system is, the more its parts depend on the whole, the more conscious it is. They even have a mathematical symbol for it, phi. A high F score means a system may be more conscious. But this raises an eerie possibility. Could complex machines, AI systems, neural networks, maybe even entire internets, develop consciousness without us realizing it, a self-awareness without a self, And if a machine claims to be conscious, how could we know if it's telling the truth? After all, you can't point to consciousness, you can't weigh it, you can't measure it in a test tube. It's not a thing, it's an experience. And that experience is always first person. It's like being inside a locked room. You know you're in there. But anyone outside, they can only guess. Even the person next to you, your parent, your partner, your child, they have their own inner world, as vivid and real as yours, but you'll never truly know what it feels like to be them. This is the privacy of consciousness, the soul of subjectivity. And it gets stranger still, because some researchers believe your sense of self is a hallucination, a useful illusion created by the brain to coordinate behavior, a simplified interface like a desktop screen that hides the messy code underneath. You aren't a continuous being, they say. You are a bundle of sensations, memories, predictions, loosely woven into a narrative, a self that exists only in the telling. But then, who's doing the telling? That question haunts you now as you drift deeper. You remember what you've passed through, the illusion of solid matter, the lies of light, the dreamlike nature of time and space. And now, even the you at the center of it all may be a paradox, a dream dreaming itself. There's a term from Eastern philosophy, Maya, the idea that the world is an illusion, not in the sense of being fake, but in the sense that it's not what it seems. Science, without meaning to, circles the same truth. Everything you see, hear, feel, it's a reconstruction. Light doesn't have color. Sound doesn't make sound. Molecules don't carry flavor. Your brain creates it all. You don't see the world. You see a model of the world generated from inside your skull, shaped by evolution to maximize survival, not truth. The real world is likely colorless, odorless, silent, a sea of waves and fields. And yet here you are, sipping tea, holding hands, staring at the stars. How beautiful the illusion. And maybe that's the final twist of the paradox. Maybe it's not a flaw. Maybe consciousness is what makes the universe beautiful to itself. That through your eyes it sees its own patterns. Through your music it hears its own echoes. Through your dreaming it tastes its own mystery. And when you close your eyes to sleep, you're not shutting the world out. You're returning inward, to the theatre of experience, to the self that both watches and performs. But even as we marvel at this mystery, a chill passes through. Because if consciousness is so delicate, so tied to biology and circuits and fragile networks, what happens when it fades? Next, we will journey to the shadowed edge of awareness, where identity dissolves, memories blur, and the self vanishes not into sleep, but into silence. Prepare now to enter the paradox of death. The path before you now narrows. It's neither sharp nor cruel, more like a long exhale, the kind you didn't know you were holding. You walk slowly and the world softens, edges blur, light mellows. You are approaching the great horizon, the one none return from unchanged. The paradox of death waits here, not to frighten, but to unveil its quiet mystery. Because here's the strange truth. Death is both an end and a process, both universal and deeply personal. And perhaps most unsettling of all, it may be necessary for life to exist at all. Let's begin at the cellular level. Every day, millions of your cells die in a process called apoptosis, programmed cell death. It's not chaotic, it's orderly, graceful, like an actor taking a bow and exiting the stage. Apoptosis helps you grow. It sculpts your fingers during development. It clears out damaged cells before they turn dangerous. In this way, death creates form. Without it, you'd be a swollen mass, or worse, cancer. Cells that refuse to die, multiplying without end, ignoring the script. And so we see the first paradox. Death is essential to life. But this programmed death is internal, quiet and microscopic. What about the great death, the one that ends consciousness, ends breath? Biologically, death is the moment the body ceases to function. Heart stops, brain shuts down, cells begin to decay. But even this is slippery. You can stop a heart and restart it. You can cool the brain and preserve it. For centuries, death was defined by breath, then by heartbeat, then by brain activity. And even now, the line is shifting. Because for several minutes after death, certain brain cells remain active, electrical signals flicker, some genes even turn on, as if trying to repair the dying body. Scientists have observed brain waves after cardiac arrest that resemble those during intense dreaming. A final surge of awareness, or just chaotic neurons? No one knows. And here we arrive at the heart of the paradox. Death is absolute. And yet we cannot know it. You cannot observe your own death. You cannot remember being dead. From the inside, death is unknowable, which is why cultures across time have filled that void with story. The Greeks imagined the river Styx, where souls paid Charon to ferry them to the afterlife. Ancient Egyptians weighed hearts against feathers. Buddhists speak of samsara, the cycle of rebirth. Some traditions promise heaven or hell, others offer oblivion, or merging with the all. And still these stories persist because the truth, if there is one, is silent. What we do know is that the brain is the last to go. You lie there, and slowly awareness contracts. Sensory input dims, boundaries dissolve. The sense of self, already a fragile construct, unweaves. This is not poetic metaphor, it is neurological fact. Near the end, the default mode network, associated with ego and self-reference, begins to shut down. The brain loses the ability to distinguish between internal and external. Subject and object blur. In hospice settings, many report patients experiencing visions of loved ones, of music, of light. Not hallucinations in the clinical sense, but consistent, comforting patterns that emerge at life's edge. Are they brain chemistry or something else? Again, we don't know. But here's a curious fact. Across cultures, many dying people report similar experiences. A tunnel, a light, a feeling of peace, a sense of being welcomed. From Tibetan monks to Western nurses, from ancient texts to modern hospitals, these patterns repeat, which raises a strange, quiet thought. What if the process of dying is itself a kind of dream? One last surge of consciousness, one final narrative, stitched from memory, emotion, biology. It wouldn't be cruel, it might even be gentle, a closing chapter written just for you. And now, shift slightly, think cosmically. All things die, stars burn out, galaxies collide, even atoms decay. The second law of thermodynamics, the universe's ultimate rule, tells us that entropy always increases. Order turns to disorder, systems fall apart, everything fades. This isn't just grim news, it's the foundation of change. Without entropy, there would be no time, no movement, no evolution, no life. Death, in this sense, is the shadow that defines the light. You are temporary. And because of that, you act, you love, you choose, you create, precisely because time is limited. If you lived forever, nothing would matter. And so, perhaps the deepest paradox is this: death gives life meaning. A philosopher once wrote, "What makes life precious is not its permanence, but its fragility." You understand this now. You think of the people you've lost and realize they are not gone, not entirely. They live in neural networks, in gestures, in stories. Their molecules become trees, wind, new breath. Even your own body, once it ceases, will return to the soil, to the air, to stars eventually. Nothing truly vanishes. Matter is conserved. Energy disperses, but being transforms. You stand now at the edge, not of fear, but of understanding. If consciousness fades with death, then your life is a miracle of presence, a candle flickering briefly but beautifully against the vast dark. And if, just if, consciousness does not end there, then it may be something deeper than matter, a quality, not a quantity, a wave, not a thing. Some scientists explore quantum consciousness, the idea that awareness may be linked to quantum processes in the brain outside time. Most of physics scoffs, but still the question lingers. Even Roger Penrose, the Nobel-winning physicist, dared to ask it. Maybe death isn't a wall, but a door. Or maybe, like waking from a dream, it's just a shift in perception. We cannot know. And yet, even in unknowing, there is peace. Because what matters most is not the fact of death, but how you live with it. You are alive. Right now, a beating heart, a dreaming brain, a mystery wrapped in breath. And soon, as we draw near the end of this journey, you'll return to sleep, not as a surrender, but as a trust, that even in darkness, the story continues. Next, we'll explore the paradox of the universe itself, the biggest riddle of all. Why is there something rather than nothing? And how, against every odd, did you come to exist? And now you are lighter than light. You drift beyond memory, beyond cells, beyond death. Nothing tethers you to the ground anymore. Not gravity, not breath, not even the weight of your own thoughts. You are an observer now, orbiting the final paradox, the paradox that contains all others. Why does anything exist at all? The very question curls into your mind like incense smoke, soft, inescapable. Not how does the universe work, or how did it begin, but a deeper, more startling mystery. Why is there something, stars, atoms, minds, time, rather than absolutely nothing? Nothing would be simpler. No space, no rules, no particles to obey them, just a perfect, eternal silence. And yet here you are, alive inside a cosmos, bursting with energy, complexity, color, a universe that sings in radio waves and organizes chaos into galaxies, into molecules, into thoughts that ask their own origin. Why? Let's look first at the beginning. The current best model is the Big Bang, a singularity expanding 13.8 billion years ago, giving rise to all space and time. But where did that singularity come from? What caused it to begin? Some scientists say it may not have been the beginning at all. The laws of physics break down at the singularity. Time may not even apply before that point. Others argue it was a quantum fluctuation, a spontaneous, probabilistic burp in a vacuum field, like particles blinking in and out of existence. And in that fluctuation, a universe was born. Still others suggest we live in a multiverse, one bubble among countless others, each with its own laws, its own constants, its own flavors of reality. Most are empty, chaotic, unlivable. But in this one, just this one, the numbers fell just right. The cosmological constant, the charge of the electron, the strength of gravity, tweaked by even a fraction, and stars would not form, planets would not cool, life would never arise. This is the fine-tuning paradox. Why are the constants of physics so precisely balanced to allow complexity? Some call this the anthropic principle. If they weren't that way, we wouldn't be here to ask. But that's not an explanation. It's a tautology. Others suggest deeper mechanisms, hidden symmetries, emergent laws, self-organizing systems. But every layer we peel back reveals another. And always beneath them, the question whispers, why something? A quirky fringe idea. Perhaps nothing is unstable. Maybe existence is the default and non-existence was never an option. Maybe there is no why, only is. Yet still, you can't help but marvel at the odds. From hydrogen to human, from chaos to consciousness, the universe has evolved increasing complexity. Stars birthed elements, elements formed planets, planets birthed life, life gave rise to minds that ask questions. This is not inevitable. This is astounding. And perhaps the wildest paradox of all is this. The universe not only exists, it knows it exists, through you, through us. The cosmos became conscious. Atoms learned to wonder, stardust rotted. E-sonnets. particles dreamed. You are not separate from the universe, you are a way it sees itself. So, what do you see? The swirl of galaxies, the hand of a loved one, the shadow of your own thoughts, the flicker of your reflection in a darkened window, all of it, all real, all mysterious. There is no final answer here, just presence, just the awe of being. Even now, scientists still argue whether the laws of physics are truly fundamental, or whether they too emerge from deeper, hidden processes. Some seek a theory of everything, a single, elegant equation that unites gravity and quantum mechanics, a thread that connects space and time and mass and light. Others suspect that ultimate simplicity is a mirage. That truth may be irreducibly complex, forever out of reach. Still, the search continues. We are a species of riddles, and maybe, just maybe, it's not answers we crave. It's the act of wondering. Because wonder is alive, it moves, it pulls us forward. It builds telescopes and composes lullabies and carves questions into stone and sky. It says, I don't know, but I want to, and that wanting is sacred. You float now above the earth, a pale blue dot suspended in a shaft of sunlight. Carl Sagan's words echo faintly through the silence. Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam. You see that mote, and you feel, against all reason, that it matters, that you matter, that against the cold silence your life is a song, brief, but infinite in its echo. And so you drift gently now towards sleep. The universe will still be here when you wake, but in this moment, this breath, this thought, this dream, you are part of it, no longer the observer, but the story itself. The stars have quieted now. Their light still dances across your eyelids. Yarn, but more faintly, like distant bells through snow. You feel it, the slow dissolve, the hush between thoughts, the final exhale. You have wandered through paradoxes, walked on the edge of science, peered into the heart of unknowing, and still, here you are, breathing, present, alive. The universe, in all its complexity, in all its contradictions, has shaped you, a being of wonder and rest, of thought and sleep. And now there is nothing left to chase, no mystery you must solve before the dawn. The questions can wait. They always do. Let your body soften now. Let gravity do the work. Your breath a tide, your limbs drifting logs in a gentle sea. Even your thoughts have grown drowsy. The voice in your head speaks more slowly, more kindly, more like a whisper in a cave. You are safe here, held in the curve of night, cradled by everything that ever was. Let go of the need to understand. Let go of the story, even let go of the self. There is nothing you must be right now, except still. The stars can keep their secrets. For you, the only truth left is this moment, and it is enough. Good night.